In this video, we'll go through the use of the TopOpt plugin to create an optimal truss and analysis in Carumba. The first step is to go download the TopOpt plugin. And you can find that on grasshopper3d.com/group/topopt. You'll find the actual component to download, the manual, which is short and informative, and the examples. So if I look at the manual, under Chapter 3, you'll see a description of tutorial examples. This is a detailed description of the example file that we're going to be using. And if I go to click on the examples link, there's a series of preset examples to explore. We're going to be using the simply supported beam grasshopper file, but we're not going to be using the 3DM file. We're going to be using the Rhino base file that was provided with the lab instead. So when you download TopOpt, a GHA file will be copied into your download folder. You just want to drag that into into Grasshopper. And that should automatically drag it and drop it on your workspace, and that should automatically copy the GHA file into the same user app data Grasshopper libraries folder that Carumba is loaded into. It should be immediately visible on within Grasshopper. So now we want to open the simply supported beam example and also open the Lab4 base file. And when you open this, the geometry will already be linked. This is basically the geometry of the beam that we're analyzing. There's a point predefined for the point load in the middle, 2 supports on either side, and you can see that one is restricted both in the X and Y axis, one only in the Y axis. And then down here are the TopOpt settings. What you're seeing is a volume fraction. So this is saying 40% of the volume of that geometry can be filled with support material. And what TopOpt will do, it will calculate the most efficient layout of that support material and leave the rest, the 60%, open. This setting down here, our minimum, adjusts the level of resolution. So the lower that value goes, the longer it might take to compute, but it will give you more fine grain of detail in its solution. Once I have all of that set up, or I could choose to reset it. For example, in one of the examples you'll see I took 4 load points rather than a single one in the center and reapplied those forces. So once I have it set up the way I want it, I toggle this run Boolean to true, double click it, it'll take a few minutes to compute. And once it does, you'll see that all of the components turn gray, the toggle turns to true, and now I can click on these and preview the results. So one option is a raster and then the vector outlines of that raster file. So this is basically giving me that optimal layout. What we want you to do in this lab is to translate that into a truss geometry and compare it with a typical Warren truss that's given and is of the same span, and see which one is a more efficient use of material. So the first step will be to actually bake these results. And you can see that I've already then tried to trace lines over the baked result, both for this point load version and then also another one where I used the distributed points and got a slightly different output for that. So you can play around with the way that you translate this. There's some guesswork involved in exactly how you want to connect those members. And then the goal is to input 2 of these, the Warren truss and one of your translations, into Carumba and test to see what the ratio is between material used and deflection. So for that, I'm going to open Grasshopper back up and I'm going to go from the simply supported beam file to the truss analysis file that's also provided. Most of this will be familiar to you. There are a few tweaks from the definitions that we've been using. The first one is that if you'll remember, for trusses, the ideal truss will only carry loads in its members axially, so no bending forces in the members, and there's a way to adjust the carumba beams to do that. One way would be to change the joints so that all of the joints are pinned connections rather than moment connections. Another way to accomplish the same thing is to drag down this modify elements, which I believe is in the model menu. Drag the modify elements component and plug all of your beams into it, and then you toggle this bending input to false. So that's going to take all of my beams and change them so that they can't take any bending forces. The other piece that you have to pay particular attention to with any of the models, but we'll kind of take time to explain it here, is how you set the restrictions on the supports, and then also restricting out of plane movement. Since we're just doing a 2D analysis, we want to restrict all of the nodes in the z-axis. So to explain the support restrictions in a little more detail, I included some diagram geometry. So what I'm trying to do with my supports is set it so that the support on the left is a roller, the support on the right is a pin. So you'll remember roller connections are allowed to move back and forth as well as to rotate around, while pin connections cannot move back and forth, but they can rotate. So this changes the types of forces that are introduced into the members. So just to visualize that, if this was my beam and I wanted a roller connection, I would want to allow movement back and forth on the x-axis, but not up and down on the y-axis, or not up and down along the z-axis. So this is translation this is translation x, y, z. I want to allow translation in the x-axis, not in y or z. When I'm talking about rotation restrictions, that's actually what you're looking at there, is rotation around an axis. So for what we want is to allow on either the roller or the pin, we want to allow it to rotate like this, so that it can rotate along those supports. And what you can see, the circle that's being drawn is actually being drawn around the z-axis. So we want to allow rotation around the z-axis, which is why this is unchecked. Just to show you what it would look like to have rotation in the other axes. Rotation around the x-axis would look like this, not what we want to have happening. And you can kind of see that in the perspective view, that when I'm rotating like this, it's going around the x-axis. And rotation around the y-axis would look like this. Again, that's not what we're trying to simulate with this structure. So this kind of explains the logic of these supports. And finally, the last piece is that since I'm only doing a 2D analysis, I don't want movement for any of the nodes. If I applied these loads without any other restrictions on these nodes, it would be like the flagpole problem that causes the model not to compute, kind of a structure hanging out in space. So I need to provide some restrictions so that these don't move up and down in the z-axis. And you can see that here. So you can see that I'm just holding all of these points up in the z-axis. So I'm not allowing translation in z, but I am allowing translation in x and y, and I am allowing rotation around z, but not around x or y. So now when I get to my output, I'm going to be paying attention to the maximum displacement, but I also want to have something, I want to compare that to the amount of material used. And the way I did that was to plug all of the curves into a length component and then add that list of all of those lengths, mass addition, and I come up with a total beam length for all of the beams in the truss. Now I copied that entire definition down and applied it to one of my top-op trusses. One important difference is that the first time I was applying a load of -10 onto 4 points. The second time I only have 3 points, so I had to divide 40 by 3 to get the equivalent load. But you'll see, and I'm using all of the same default member sizes. I'm not adjusting the material or the cross-section at all, so I'm just getting a default value there because all I'm trying to do is compare the efficiency of the shapes. And you'll see that if I multiply these two together, the displacement times the total length of material used, you can see that the top-op generated truss is a little bit more efficient than the Warren truss. Another helpful visual, just to look back at the way the supports are working and make sure my beams are only carrying loads axially. If I plug in my normal forces from my beam view, I get all of these values. If I plug in any of my moment forces, these are all 0 because it's not carrying any moment. So I know that's working. And then finally, just to show you how those connections impact how those support restrictions impact the values. If I turn this back on to true so that these members can now bend again, you'll quickly see the difference. If I restrict rotation, you can see that it kind of bends that member in a different way. Or if I restrict translation on the roller, you can see it kind of squishes the entire truss and again bends the member in a different way. So for a simply supported beam, it's important to get these right. The first step of the lab is to repeat this process to play with top-op, generate some trusses, compare them. The second step is to find a precedent, a bridge or a building facade, something that you would like to try to improve through the topology optimization, and try to simulate the supports and the loads, come up with a geometry and do the same kind of comparison of the existing system to your top-op generated system, using the same definition to see which is the more efficient use of material according to the displacement. One tip when you're now looking at precedents, you have to be careful with the scale in top-op. So when I've drastically changed the scale of this base definition, I've sometimes had problematic results. I think it has to do with the resolution of the pixels that it's analyzing. So I would recommend that you try to simulate the proportions of your precedent without changing the scale very much. And then, of course, once you get the load pattern, you can adjust the scale so that you're analyzing the actual scale of the precedent with Karumba. So this load pattern is in some ways scale-less. It's just giving you a distribution pattern that you can then scale up or down to match your precedent.